So the idea of this video is to go through all the theoretical learning outcomes from Physics 153. There are 12 learning outcomes that we've encountered so far in the course, and I'm going to just march through all 12 of them pretty much in order and describe a kind of situations in which these guys arise and how to think about them. So the first theoretical learning outcome, TLO number 1, let's say TLO-1, is to use the momentum principle to compute the future motion of a system given its current state. So first of all, what is the momentum principle? It's that the change in the momentum of a system is equal to the net force acting on the system at some point times the time over which that net force acts. While it's a fundamental principle, this one is approximate, but the approximation is a good one to the degree that the time interval is small enough, it's a short enough time interval, that the force doesn't change appreciably during that small time interval. If you need a more accurate version, I guess, an exact version, you could take this to the limit that the time interval goes to 0, in which case another way to think about the momentum principle is that it's the time derivative of the momentum. The instantaneous rate of change of the momentum is equal to the net force. So that's another way we write it. Now, TLO-1 is about using our knowledge of the force now and the rate of change of momentum now to predict the momentum in the future. So how that might work, say, for example, we know the force is not changing quickly. It's a relatively slow changing force, or maybe it's a constant force. And then you could say that, well, the change in momentum is the final momentum minus the initial momentum. And if you know the net force and you know you're going to wait for some particular period of time, you can then use this to solve for the final momentum. Say the final momentum is going to be the momentum now plus the change in momentum, which is going to be the net force times the change in time. So this is a sense in which you can predict future motion given your understanding of the current situation, the net force acting at this moment in time, and the current momentum, the momentum at the beginning of the time interval. The other thing that we need to be able to do, of course, is to predict what happens to the position of the thing. And so once you have the final momentum, the other thing we often do is to use the change in the position of a particle divided by the time. That's equal to, it's the average velocity, of course, but we also often say that that's approximately the final momentum over the mass. In an iterative calculation, when you're going through many steps and they're small steps, it's often convenient just to use the final momentum divided by the mass as an approximate value of the average velocity. And then you get a similar relationship for the position. You know that the final position is equal to the initial position plus the change in position. But we can use this guy to solve for the change in position, and we get that that's the initial position plus the final momentum divided by the mass times the change in time. So these two together are update principles or update formulas that we can use in an iterative calculation to calculate where something is at a later time, given that we know the force acting on it now. So that's the idea. Okay, so what about TLO-2? TLO-2 is sort of the other side of the coin. It says to use the momentum principle to infer forces acting on a system given the current motion. So the idea here is you still use the momentum principle. So you still say, for example, that delta P is F net times delta T. But now maybe you know the change in momentum and you know the time interval, but you don't know the net force. So the idea there is to simply solve for the net force if you know the current momentum and say maybe the final momentum and the initial momentum and the change in time, you can calculate the rate of change in momentum, and that means you know the net force. Now, sometimes you know, so for example, excuse me, suppose we have a mass hanging on a string, so we have a mass here hanging on some kind of a thread, and we know that the force of the Earth acting on the mass, is equal to mg, right? So that's going to be minus, it's going to be let's write it as mg vector, where g vector is a downward pointing vector. But we don't know the tension force, the contact force of the string acting on the mass, but we know that the mass is just sitting there. So we know that the rate of change in momentum is 0. And that means that the tension force plus the force of the earth acting on the guy, those guys have to add up to 0. So that means that the tension must be equal in magnitude to the weight. So that means the tension is just equal to mg. So there's a case where you're inferring a force, the tension in the string, by using the momentum principle and the known motion of the object in order, and the known weight acting on the object to infer the force of tension. So that's another way you could use this TLO. Now that brings up another TLO, which is TLO-3. And that is just the ability to draw free body diagrams. I just drew one, but it wasn't a really good one because I should have added here, this is the string acting on the mass. So a free body diagram is just a diagram that shows all the forces acting on the system with labels and correctly drawn. So for example, suppose, go back to the pig experiment we had where we had a pig flying in the room. It had eyes and legs and ears, I guess, anyway, and wings. So there's a pig flying around in a circle. It was really tied to a string. And we needed to be able to draw a free body diagram of the pig. So here's the free body diagram. It's got a pig here. It's got the force of the earth acting on the pig. That's the weight. That's the earth acting on the pig. I'd call that Fg maybe. And then there was a tension in the string, like this. So that's the tension, which is the string acting on the pig. So a couple things to notice. The forces both have their tails acting on the dot that represents the system. The forces both have labels that show the source of the force and the object experiencing the force. So the string acts on the pig, the earth acts on the pig. All forces have sources, so that's basically all there is to it. Once you have an expression or a free body diagram like this, then you can use it to direct your solution to the problem. You use it to for example, you could use it to correctly write down the momentum principle. In this case, the momentum principle would be that the rate of change of the momentum of the pig is equal to the net force. Well, that's the force of tension plus the force of gravity, the force of the earth acting on the pig. Of course, we would want to break this into components, but that's a different TLO. But the TLO-3 is just the ability to correctly draw a free body diagram. Okay, so and we'll come back to this example in a minute. Let's look at TLO-4. TLO-4 is to compute forces directly due to fundamental interactions. Well, so far in this course, there are only two fundamental interactions we've encountered. There's the force of gravitational force, so Fg, and that one is minus capital G mass 1 times mass 2 over the distance r12 magnitude squared. So r12 is the vector that goes, it's the magnitude of the vector that goes from mass 1 to mass 2. And then there's r12 hat. So what would I draw here? I'm going to say, here's mass 1, here's mass 2. R12 is going to be a vector that looks like this. So that's R12 vector. There's a unit vector in the R12 direction. I call that R12 hat. That's this guy. And this is the force, the gravitational force of mass 1 acting on mass 2. So if I were going to write it out completely, that would be the way I'd write it. Now there's a similar force. It's the electrostatic force. So say Fe maybe. And I could have charge 1 acting on charge 2. It's exactly the same picture. I've got charge 2. I've got charge 1. I've got a vector R12. I've got a vector R12. Let's see, that's not right. Hang on a second. I've got a vector R12 hat, okay? And the only difference is that the equation is slightly different. The electric force of 1 acting on 2 is going to be, in this case, it's plus 1 over 4 pi epsilon 0. Seem to have gotten my line a little bit fatter than I need it. And then it's going to be Q1, Q2 over magnitude R12 squared, R12 hat. So it's almost exactly the same formula, except what's changed, the constant out in front is different. Here the constant is negative g. Here it's 1 over 4 pi epsilon 0. Here the two charges produce the force. Here it's two masses. And everything else is identical. So these are the two TLO-4 examples that we'll be using in this course. One thing I want to point out is that understanding this formula is about calculating the force, but it's also, if you know the force, if you can estimate the force, then you can also use this formula to go back and estimate other things. For example, if we can go back to TLO2, if we can infer the force from the motion, and we know the force is produced by, say, gravitation, then we can go back and estimate the mass of one of the objects. So, for example, if we have a satellite orbiting here we have an asteroid, we have a satellite orbiting the asteroid, we can use the motion of the satellite, say how long it takes to go around and the radius of curvature of the orbit, to estimate the rate of change in momentum of the satellite. Then we can know that the only force acting is gravitational force, and we know the mass of the satellite, for example. Then we can go back and infer the mass of the asteroid. So you can use this formula in a lot of different ways. The most important thing for TLO4 is that you know how to apply it in different situations to see how the force relates to the masses or charges and the distances and so on. And you can calculate the force in different situations. And that also implies that you know how to do, calculate the R12 vector, calculate R12 hat, things like that. Okay, let's go on to TLO5. TLO5 says compute forces arising from contact interactions. So we already did one of those in the earlier example. So if I go back up to the mass on this string here, that string force is a contact force. It's a force of one object in contact with another object producing a force. We inferred the string force. That would be an example of TLO2, but then understanding what the string force is and how it works, that's TLO5. Okay, so TLO5 is about contact interactions. It also includes things like a spring interaction will be a contact interaction. A sliding friction interaction will be a contact interaction. Anytime a normal force. So if I've got a mass sitting on a table, right, there's a force between the table and the mass. So that would be F, I'd say Fn. It's the table acting on the mass. And then, of course, there's the Earth acting on the mass. So you could call that Fg. That's the Earth acting on the mass. You could say that the momentum principle demands that the rate of change in momentum is equal to the net force. Well, that's the normal force plus the gravitational force of the Earth pulling down. And we also see the mass is just sitting there, so the rate of change in momentum is 0. If we take the y component of both of these guys, that's got to be the normal force minus mg equals 0. And that tells you that the normal force in this example is just equal to mg. So that's an example of calculating. It's a TLO2 because we're inferring the normal force from the momentum principle, but it's also a TLO5 in a sense because the normal force is a contact force. So that's TLO5. All right. Also, if the mass were sliding, say, for example, sliding to the right or sliding to the left, TLO5 would involve the calculation of those frictional forces. So the frictional force, we know if something is sliding, it's mu k times the normal force. If something is not sliding, if it's stuck, then we know the frictional force is less than or equal to mu s times the normal force. Remember, mu s is the coefficient of static friction. Mu k is the coefficient of kinetic friction. So this is the sliding case. This is the not yet sliding case. The less than sign simply means that the frictional force, if it's not sliding, we know that it's not any greater than mu s times n. Mu s times n is the limit. That's the maximum value of the static friction you can have before it starts to slide. So that's that idea. TLO-6, this is probably one of the trickiest ones in terms of keeping things straight. This is relate concepts between microscopic and macroscopic objects. So this goes back to our ball spring model of matter. So we think of matter as a bunch of little chunks of mass connected by springs. And, we did a bunch of experiments related to this, and we also have solved a lot of problems. But the main point is that there's a connection between the microscopic spring constants between atoms and the masses of the atoms, and then the macroscopic material. So if you have a string or something like that, or a wire, you think of it as being made up of a bunch of atoms. The atoms, there's a certain density to the material, so the density is mass per unit volume. The atoms each have a certain amount of mass and a certain size, so we think of these guys as having a spacing between atoms. The spacing we just usually call d. Okay, it's also sometimes called the diameter of the atom, because it turns out if you allocate each atom a certain space, a certain distance that it occupies, that also works out to be d. It turns out that the mass of a single atom divided by d cubed is also equal to the density. So if you know the density in mass per unit volume and you know the mass of a single atom, you can solve that for d. I'm not going to do that here, but there are lots of examples. You could look at some past quizzes you did to see how that calculation works. The other thing we worked out, and again, I'm not going to go through the thing in detail, but there's a connection between the Young's modulus. So when you hang, let's say we hang a weight on this thing, some mass, so we end up with a downward force, a tension in this thing of mg. The thing is going to stretch a little bit, the amount of stretch, we'll call that delta L. If the total length of the wire initially is L, then the idea is that there's some strain there. So there's a strain delta L over L. It turns out that the strain times the Young's modulus, which is a modulus of elasticity, is equal to the stress. The stress is the force per unit area. So the area is like the cross-sectional area of the wire. The force is like the force pulling down on the wire. The ratio of those two, the force per unit area, is the stress, and it turns out that's proportional to delta L divided by L. The proportionality constant has units of stress, so units of stress, and that guy is called the Young's modulus. So it's sort of like a macroscopic spring stiffness. It's sort of proportional to the stiffness of the wire, but it's also related to the spring constant of the material, the interatomic bond spring constant. In fact, let's see, I think the way it works is the spring constant, so KSI, the spring constant is like a normal number, like 10 newtons per meter or something that we've seen in the lab. The Young's modulus is a huge number. It's got units of force per unit area, and the distance between atoms is a very small number. So just to help you remember, you take a very small number like the distance between atoms or the diameter of an atom, you multiply it by the Young's modulus, which is a very large number with units of newtons per square meter, times a small number, which is meters, you get newtons per meter. So if you forget the formula, you can sort of figure out what it has to be based on the magnitude of the various pieces that go into it. All right, so that's TLO-6. TLO-7, this is, I should say, this is another challenging one, and it really has two pieces. So this is about curving or oscillatory motion, which are two different things, but they're slightly related. And so I'm bundling those into a single TLO. The first idea is that if you have curving motion, so you have something moving in a curve, it's going to have a momentum that's changing, and the momentum is changing because at the very least its direction is changing. So I've got some initial momentum here, I've got some final momentum here. If I bring these two guys together, if I think about the initial momentum pointing this way and the final momentum pointing that way, say, the change in momentum is a vector that looks like this. So this is P initial, This is P final. This is delta P. Now, delta P is doing two things. It's changing the direction. So it changes the direction of the momentum and it changes the length of the momentum. And I want you to notice that the change in direction of the momentum is produced by the perpendicular component of delta P, and the change in the magnitude of the momentum is produced by the parallel component of delta P. So delta P parallel produces change in magnitude. It changes the magnitude of the momentum. Delta P perpendicular changes the direction. So that's an important insight. And I would say 90% of the time in this course, because of the nature of the problems we end up solving most of the time, in problems where things are moving in a curved motion, the momentum has a constant magnitude, but the direction is just constantly changing. So examples of that include the pig we saw before. You know, you've got the pig on a string. It's got two forces. It's moving in sort of a conical pendulum kind of a thing. It's moving at a constant speed in a circle. Another example is the spacecraft orbiting the asteroid. We just talked about that one too. You've got a spacecraft here. It's got a force acting toward the force of gravity acting toward the center of the asteroid, and it's moving in a constant circular motion. In the pig case, we've got the tension. That's the string acting on the pig. We've got the force of gravity, which is the earth acting on the pig. But the pig is actually moving in a uniform circular motion. In both of these cases, the rate of change of momentum only has a perpendicular component. The rate of change of momentum points toward the center of the circle in the direction of the net force. So you write, let's do the pig here. So this is the pig. So the rate of change of momentum is equal to the net force. Well, that's the tension plus the force of gravity, right? And we break that into x and y components. So let's say in the x direction, what have we got? We've got, well, the rate of change of momentum in this picture, it's going to be minus p v over r, the magnitude of the momentum times v over r. And in the x direction, what have we got? Let's assume that this angle is theta. That means this angle is theta, something like that. So I'm going to say that and this angle is going to be 90 minus theta. So you could either write this as minus t times the cosine of 90 minus theta, and then you could say there's no force from the Earth in the x direction, so that would be it. Some people might write this minus t sine theta, same thing. Okay, what about the y direction? In the y direction, there is no rate of change of momentum because the pig is not moving vertically, so this would be 0. And then what would we have here? We'd have t cosine theta in the positive y direction, and in the negative y direction, we've got minus mg. So the point is we end up with two equations here. We've got the momentum principle, but the key idea is that you know how to calculate the rate of change of momentum and put that into the momentum principle in order to solve the problem. So anyway, that's the idea. Now the key here is to notice that these two equations basically boil down to t sine theta. I'm going to go ahead and put in p is equal to mv since it's not a relativistic pig. So this is going to be mv squared over r, and then t cosine theta is mg. And you'll notice if I take the ratio of these two equations, the t's cancel on the left. I just get I get tan theta on the left. The m's cancel on the right. I get v squared over rg on the right. And so you can see that it's easy to relate the motion of the pig, the velocity of the pig, say, with the angle and the radius of the circle. One thing to notice here is the radius of the circle, of course, is not the length of the string. It's the length of the string times the cosine of 90 minus theta or something like that. But anyway, the key is to note that it's moving in a circle, and since it's moving in a circle, I know the rate of change of momentum. Okay? Look, this is exactly the same problem. The object in the asteroid, what's the difference? So if I have an asteroid here and I have an object orbiting the asteroid, right? I still have the momentum principle. It's dp dt it's going to be equal to the net force. But the net force is, of course, the force of gravity. That's the asteroid acting on the spacecraft, right? So this is the asteroid acting on the spacecraft. And I can simply write that down. Let's take the component of the force pointing toward the asteroid. So dp dt, it's still going to be pv over r, pointing toward the asteroid, and there's a force pointing toward the asteroid in the same direction. So this has to be g times the mass of the spacecraft times the mass of the asteroid divided by the radius of the orbit squared. And I can put in the momentum here. I get mv squared over r. I get g m asteroid over r squared. The mass of the spacecraft actually goes away, and I get a simple, I got two different cases of r. Well, these two r's are the same, huh? So I get v squared is equal to gma over r, and then v is the square root of that. So I can calculate the speed of the asteroid as it goes around. If I know the radius of the orbit, I know this also is the velocity, so that's going to be 2 pi r over the period of motion. So I can use that to calculate the period, the time it takes to go around, or whatever. So anyway, that's the curving motion part of TLO-7. The other one is what happens when you put a mass on a spring, say, and you let it wiggle. So it's wiggling up and down. This one, it's more difficult to relate directly to the momentum principle without going through a fairly long derivation. I'm not going to do that right now. I'll just point out that what you find is that the solutions to this problem, if you ignore any kind of damping or friction, are sines and cosines. So you get sines and cosines that go up and down like this. And what's the main point? The main point is that if the period here is t, and the spring constant is k and the mass is m, that there's a relationship omega, which is the angular frequency, which is 2 pi divided by the period, is just the square root of k over m. So, and the mass just oscillates forever with a certain, with whatever starting amplitude you give it. Say if you started at rest at some stretch, it's going to just wiggle up and down with an amplitude that is just equal to that initial stretch that you give it. I'll come back to this in a minute when we talk about energy. In a situation like this, the energy associated with gravitational interaction with the Earth plus the elastic interaction with the spring plus the kinetic energy, the sum of those three guys has to always add up to the same number. If there's no damping, there's no interaction with the surroundings. And so that makes it easy to solve problems involving like initial conditions and things like that. So these two, the curving motion, oscillatory motion, are TLO-7. So TLO-8 is about energy. So let's talk about that. It says, compute the change in a system's energy based on the initial and final state. So this one's quite easy. The energy principle, of course, is what this is all about. The energy principle being that the change in the energy of the system is equal to the work done on the system by the surroundings. So the surroundings act on the system. Plus, you can also have heat transferred to the system from the surroundings due to a temperature difference. And plus, there can also be some other things here like radiation, etc. But many of the time, these guys aren't really significant. So we focus a lot of the time, I should say, chapter 6, certainly, we just focused on mechanical work on the system by the surroundings. But as we got into chapter 7, we added heat transfer and so on. But this TLO-8, it focuses on the left-hand side of this equation. So what is the change in the energy of the system? Well, the system can have kinetic energies, so there's changes of kinetic energy. There are various changes of potential energy. It could have gravitational potential energy, you could have elastic potential energy, other kinds of potential energy in the system. And you can also have internal energy like thermal energy. So you could say delta E thermal if the system's temperature is changing. So TLO-8 is just about this left-hand side here, calculating these changes in energy of the system. And of course, you might not know the initial and final state of the system, so some of these initial and final state energies may have variables in them that you need to solve for later. But the TLO is really about, can I write down the change in the energy and can I come up with an expression for the change in the energy that makes sense and that works? So that's TLO-8. TLO-9 is the other side, and it's primarily about work. So it says compute the work done on a system by a force or the energy transfer between a system and the surroundings. So it's about the right. So TLO-8 is about this part. TLO-9 is about this part. Okay, so calculating work. Of course, you know that the work done by a force is just equal to the force dotted into the displacement. So that's a mechanical mathematical process. Do I know how to calculate a dot product? If there are multiple forces acting, they each might do work. The other thing that shows up in TLO-9, when we get into chapter 9, you know that we encountered this notion of the point particle system and the extended system. So in the point particle system, the work done on the system is equal to the net force dotted into the change in the position of the center of mass. So this is in the point particle system. That's the way you calculate the work. In the extended system, you literally have to take each force that's acting on the system and multiply by the displacement of the point of interaction of that force. So if the force acts on, pulls on a string or pushes on the edge of the box or whatever, it's the actual displacement of the point of contact of that force, not the displacement of the center of mass. So if I take the extended system, the work done by a single force is literally the force dotted into the displacement of the point of contact. So I'm going to put here point of contact of that force. So F1 would be W1 would be F1 dotted into the point of contact of force 1. And if there's another force, it would be force 2 dotted into the displacement of the point of contact of force 2 for the extended system. But TLO-9 is all about the right-hand side of the energy principle. And finally, TLO-10, this is use the energy principle to make inferences about the initial state, final state, work done, or energy transfer between a system and its surroundings. So basically, that's using this whole energy principle concept to make inferences. So for example, how high does a particle go up in the air when I throw it up? So I'm going to write down the energy principle here. Change in the energy is equal to the work done on the system by the surroundings. And in this case, maybe I would include the Earth in the system. So the change in the energy is going to be the change in the gravitational potential energy plus the change in the kinetic energy equal to the work done on the system by the surroundings. And if I include the Earth in the system, this is going to be 0. So TLO-9 is easy in this case. It's just 0. TLO-8 is the change in the gravitational potential energy. So that's going to be mgh minus 0. That'll be the change near the surface of the Earth. The change in the kinetic energy is going to be 0 minus 1/2 mv squared, v0 squared, and that's going to be equal to 0. So the left-hand side, this is TLO-9, evaluating this. The right-hand side, TLO-8 is the left-hand side. TLO-9 is the right-hand side, essentially. And then TLO-10 is solving for the height. So the point is the m's are going to cancel. I'm going to get the height is equal to v0 squared over 2g, I guess. So the point is, using the energy principle to make inferences usually just means solving the equation, the statement of the energy principle, in order to find something you didn't know before. So TLO-10, but in different problems, it can be more complicated than that, because depending on what you know and what you don't know, you might need to actually include other information like the momentum principle, something like that. But TLO-10 is about making those inferences. Okay, TLO-11 This is apply the energy principle in extended systems where multiple forms of energy, rotational, vibrational, thermal, are essential. So TLO-11 is really just TLO-8, 9, and 10 bundled together, especially in those situations where you have extended systems. So this would be the kinds of problems you're going to encounter in Chapter 9 a lot. So what does that include? So that's going to include things like rotational kinetic energy. It's going to include vibrational kinetic energy. It's going to include, situations in which you've got to deal with the point particle system and the extended system together to solve a problem. So one example might be, suppose I have a chain that's all piled up on the ground, and I grab one end of it and I pull. And after I pull a while, the chain stretches out, and then it's moving to the right with some speed. The final, after I pull, with some net force. And so let's say I pull a distance d here. And the point is, I could use the point particle system to calculate the change in the translational kinetic energy of the system. So let's say in the point particle system, the center of mass goes from here to here. So that distance is d over 2, right? And so what I would say is that I'll write down the energy principle for the point particle system. The change in the energy point particle system is equal to the net force acting on the system, that's this F, dotted into the displacement of the center of mass, which is going to be, if I think of d as a vector like that, it's going to be d vector divided by 2. And what is the change of the energy in the point particle system? Well, that's just the kinetic energy of the center of mass, or the translational kinetic energy. So that's delta K trans, and that's going to end up being FD over 2, right? Then let's write out the real energy, the full energy principle, and that's going to be equal to the work done on the system by the surroundings. And what's the change in the energy? Well, there's going to be the change in the translational kinetic energy, and there's going to be some change in thermal energy, right? And that's going to be equal to the work done by the force at the actual point of contact, which is going to be FD, because the actual point of contact moves a distance d. And so we get the change in the translational kinetic energy we already figured out, FD over 2. The change in the thermal energy is equal to FD. So you can see that means the change in the thermal energy, delta E thermal, must be also FD over 2. So that's a way you can apply the point particle system and the energy principle to solve a problem. This doesn't involve rotation or vibration, but it does involve thermal energy, and most importantly, as far as TLO-11 is concerned, it involves the point particle system and the extended system. So TLO-12 and 13 we're going to skip for now because those are from later chapters we haven't encountered yet. TLO-14 is to apply the energy principle in a case where the energy is quantized. And so these kinds of problems, the concepts involved here, so we say we have an atom with 3 energy levels, E1, E2, E3. It's just understanding that the energy can only have one of these 3 values, and so transitions occur between these energy levels, and when those transitions occur, it means that energy is transferred into the system or out of the system has to be integer multiples of these energy differences. So for example, if the system goes from E1 to E2, it's going to absorb energy from maybe a photon, and the electron could jump from E1 to E2, something like that. Or if the system is in state E2, it'll emit a photon whose energy is equal to the difference E1 minus E2. All right, so that's it. That was a very quick rundown of all the TLOs for this point in the course.